Hello friends. So today we are going to discuss few problems, four problems basically, and these four problems will be from the you can say from rotation. Okay, and the first question we have, and it states that a rigid massless rod of length L connects two identical particles, each of mass m. The system lies on a smooth, frictionless horizontal table. A third particle of mass m, moving with velocity v0, strikes one end of the rod. After the collision, the incoming particles rebound straight back along its original line of motion. Assuming the collision is perfectly elastic, that is, energy is conserved, determine the angular speed of the rod about its center of mass immediately after the collision. So this figure is there, but I forgot to paste it. So basically we are given that we are having two mass and they are connected by a rod whose length is of L. Okay, and suppose this is a mass, first mass, and this is a second mass. Okay, so this is mass A, and let us call this as a B. And with the horizontal, it is making the angle of 45 degree. Okay, so this is our basic question, and it is also given that there is a third mass. Let us call this as C, and which is going to strike our mass A. And so we have to find out the velocity of the angular speed of the center of mass. Okay, that is required to find out. So let us suppose the center of mass is somewhere here, and it is going to rotate something in this direction. And so it is given that there is no friction anywhere. So in this case we have three masses, each of three of you can say particles, each of mass m. So let us understand the coordinate geometry of this entire system. So in this case we assume that it is placed in the xy plane, and the particle A is at the one end, and so let us, this is the center of mass, and you can say that position of the center of mass respective to particle A, let us call this as RA. So this position vector we are calling it as RA, and from B we are going to call it as RB. And let us So we can say that the center of mass of the rod system is at the midpoint of the rod. And therefore we can write that our position vector from our center of mass to particle A, let us call this as our RA, and this RA will be nothing but our the horizontal as well as the vertical coordinate. Okay. And the total length is L, so we have this entire length is of L, so this L by 2 and other portion will be also L by 2. Okay, so we can say position vector will be equal to over L by 2 and cos of 45i unit vector, cos of 45i unit vector plus sine of 45 j unit vector. And with cos and sine is 1 by square root of 2, so this comes as our L 2 root 2, and we get this as I plus j. And similarly we can say for particle B, let us call this as R vector, and that will be obviously negative of our RA, and this will be minus L by square root of 2 I unit vector plus j unit vector. And we can also find out the moment of inertia about the center of mass. So we can say moment of inertia of the system about center of mass, let us suppose that is our I, and that is equal to mass of our A and distance square plus mass of our B and that is distance square, because distance is same from A as well as B. Therefore we can say that our I is equal to, we can write this as our 2m r square, and in terms of L we can write this as L by 2 whole square. So this gives us 1 by 2 ml square. So this is the moment of inertia of the our center of mass. And now we come to our, you can say, it is mentioned that the incoming particle rebounds straight back along the original path. Okay. So it means that the impulse that is being delivered is entirely during the collision is purely along x-axis, x direction rather. Okay. So we are given that incoming particle rebounds straight back along its original path. Along its original path, and original path we already discussed that it is along x axis. So from here we can say that the impulse delivered during collision is purely along x direction. And it means there is no y component in it. So you can say no y component. And so it is also given a question that the rod is rigid and at an angle of 45 degree. Therefore, the collision at A will result in both the translational motion as well as the rotational motion of the system. So we are given that our rod is rigid so which basically means that we are going to have translational plus rotational in the system. And system here means a rod plus A plus particle B. So this consists of entirely the system. And our particle C is moving along x-axis. Therefore, we can say that our initial velocity of particle C, initial velocity of C, we can call this as our V naught I unit vector, and we can say that the impulse from C to A, impulse from C to A, let us call this as J unit vector, that will be equal to J and our I unit vector, okay, because it is in x direction. Okay. Now we come to after collision. So after collision, it is said that our particle C, or it moves back with the same, it rebounds back in the same direction. Okay. And therefore so here we are not interested in particle C, so we can just simply remember that it is going to rebound back in the same direction, and later on if required we can just use its velocity component if required. Okay. And we are mainly interested in the mass A as well as mass B. So this we can say that the total mass of the system total mass of our system is our 2m, and the impulse is our ji unit vector. Therefore, we can say that the center of mass velocity after collision, let us call this as our VCM, and this VCM will be equal to our J divided by 2m, and this is our I unit vector. And along with this, the impulse is also going to cause angular result in angular we can say angular impulse about the center of mass. Therefore, we can find out the and okay, so based on this, we can find out the torque arm for the impulse A, and respectively we can find out the torque arm for the our B also. Therefore, we can say that impulse causes angular impulse about center of mass. And like we said, that since J is along our x-axis, therefore the RA is going to have a component along x-axis as well as the y-axis. Therefore, we can write that the angular impulse it can be written as our RA and our J vector. And we already know our RA is our L upon 2 square root I plus J unit vector, and our J is along I direction. And from here we get that this angular impulse will be equal to our one will be our I cross I and other one will be our J cross I. Okay. So J cross I will be giving us minus of K. So this will be minus L J divided by square root of 2 and multiply by our K unit vector. So we are only interested in the magnitude part. So therefore we can say that its magnitude will be, it can be given as Lj and 2 root 2. Okay. Therefore, we can also say that the angular momentum about the center of mass is nothing but I multiplied by our omega. And we can say that our angular momentum about the center of mass is our I times omega, and that will be equal to our minus Lj, and this is our 2 root 2. And from here we can find out our omega. So we can say our omega will be equal to minus Lj 2 root 2 times I. I is our moment of inertia, which we have already calculated. So this comes minus Lj 2 root 2 times 1 by 2, and this is our ml square. And here this 2 goes with 2 and square goes by our L. Therefore, we get that the value of omega is equal to negative of our j, and this comes as our ml square root of 2. Square root of 2 and our ml. And this negative sign is representation of only direction, and we are only interested in our magnitude. We can just take that later on also when we are going to require it. Now we come to our conservation of angular, this all linear momentum as well as the angular momentum. And okay, let's discuss first of all the conservation part. So you can say conservation laws. And it is given that the table is frictionless and the entire impulse force is in x direction. There is no direction force in y direction, but and also the impulse is only in x direction. So we can say that we can divide the momentum in x and y component, but merely we are interested in, you can say, our x component because everything is moving in x direction. So you can see initial total momentum, initial total momentum, that will be equal to m v naught I unit vector, and our final we can write this as m, and we have this as vc prime plus twice m and velocity over center of mass. And we can find our velocity of our this particle, that is c particle. Okay, so that is quite easy to solve also because it is given. Let me solve in this part. So it is said that our vc is, so you can say velocity of c, which is our vc, which will be equal to our its initial velocity minus j upon m. Okay. And we know that our from here we can find out the change in momentum. So we can see our change in momentum, that is delta pc, and delta pc will be equal to our minus j I unit vector. Therefore, we can write that m times vc prime is equal to m v naught minus j. And therefore, we can write that our velocity vc prime is equal to v naught minus j upon m, which is our required part. Okay. And now we can just substitute it. So we get this as our m and our v naught minus j upon m plus twice m, and velocity of center of mass we also know is our j upon 2m. So this comes as j upon 2m, and here this 2m and 2m cancels out, and okay, so we simply multiply the m inside. We get this as m v naught minus j plus j, and this minus j plus j cancel out, so this comes as our m times v naught. So this is our final angular momentum. Okay. And this also tells us that there is a conservation of our momentum also. Okay. Now we are going to use energy conservation. For energy conservation, our initial energy is our, rather we can say initial kinetic energy. Initial energy, that will be our kinetic, and that will be equal to our half m v naught square, and final kinetic energy, and that will be equal to kinetic energy of particle C plus kinetic energy of rod system. And our rod system will be both translational as well as the rotational. And kinetic energy of C is quite simple, so we can write our kinetic energy of our C will be equal to our half m Vc prime whole square, and Vc prime we already know, so this comes as half m v naught minus j upon m and whole square. And now we come to the kinetic energy of the rod system. So we can say our kinetic energy of rod system, that will be rotational plus translational, and we get this as half 2m and Vcm square plus half I omega square. Therefore, we can say, or rather we can say, we know that our Vcm is equal to our j upon 2m, and so we substitute it in this equation, so we get this as half twice m j upon 2m whole square, and this will be coming as j square upon 4m, and moment of inertia we also know, that is our value of I is our half ml square, Therefore, and omega also we know that our omega is equal to j upon square root of 2 ml. 2 ml. Therefore, we can calculate the second part. So we get our half I, and this is j upon square root of 2 ml whole square, and we get this as 1 by 4, and m square and goes away, l square cancels out. Therefore, this second part will be giving us 1 by 8, and our j square and l square goes away, we are left with only m. And what else is left? Okay, so we are almost done. So we substitute in the conservation part, and we get that conservation, which gives us initial energy is our half m v naught square is equal to, and this is our half m v naught minus j upon m whole square plus first part is j square upon 4m plus second part is our j square upon 8m. Now we can just solve it and expanding also. So we get this as our half m v naught square is equal to half m, and we have this as our v naught square plus j square upon m square minus this comes as our 2 v naught j upon m plus, and this second term we can solve it. We can take LCM as our 8, so this comes as 8m, and this will be our 2 3, so this will be 3 j square. And okay, so we are interested in solving this part, so we multiply by half m, so this gives us half m v naught square plus this comes as half m, and this will be g square upon m minus this comes as our half goes by 2 and v naught j plus 3j square upon 8m, and this is equal to half m v naught square. Now okay, so these two terms cancel out, quite easy. Okay, no problem. And obviously j cannot be equal to 0, so we can just remove one of the j's, and we are left with this as our z. Let me do it other way around, and we are left with this our half j upon m minus v naught plus 3j upon 8m is equal to 0. And we can combine these two terms, and this gives us, we can take our 8m as a LCM, and this will be coming as 4 plus 3 is 7. So this comes as 7j is equal to our V naught. So from here we can say that our j will be equal to 8 by 7 m V naught. And omega, we know the relationship between omega and j. So we know that our omega is equal to j upon square root of 2 times ml. So this is our 1 by 2 ml times j is our 8 by 7 m V naught. And our m and m cancels out. So we can also rationalize it. So this is going to solve it further. So this comes as 2 goes by this and this goes by 4. So we get our omega is equal to 4 root 2 divided by 7L times V naught. So this is our angular velocity which we are supposed to find out. Come to the next question. Okay. So next question states that a child of mass m runs on a smooth ice with a horizontal velocity v naught and steps on the end of a uniform plank of length L and mass m. The plank initially lies at rest on the ice and is oriented perpendicular to the child's lines of motion. Neglect all friction between the plank and the ice. So based on this, we have two questions. Describe quantitatively the motion of the system, that is child plus plank, immediately after the child steps onto the plank. Part B, there exists one point on the plank that is momentarily at rest just after the collision. Determine the location of this point relative to the center of the plank. So in this case, we can just draw an approximate figure, and suppose this is the plank, and its length is given as L, mass is given as capital M, and we are given that the child is running. Suppose the C is the child and it is running in this direction, okay, and steps on it, okay, and its velocity is given as our v naught and mass is given as small m. So we have to define the, we can say, the motion of system, that is child plus plank. Okay. So obviously the combined system, that is child plus plank, will be consisting of two components. The motion will be consisting of two components. One will be our translational motion, which is about the center of mass, and other one will be also the rotational motion about its center of mass. Okay, because we know if there is no pivot point, then everything revolves around the center of mass. So let us define our, you can say, coordinate system. And for that, let us assume that this is our x-axis and y-axis, and this is our origin. So the initial velocity of the child is along x direction, so we can call this as v naught I unit vector, and plaque is at initial, and the collision is taking place at this point, which is our origin. And we are going to start with the conservation of the momentum. So let us write conservation of our linear momentum. And the initial linear momentum is only because of the child, because the Planck is stationary. So we can say initial linear momentum it is our pi, which will be equal to our m v naught I unit vector plus 0. So we get our initial linear momentum is our m v naught I, and after the collision the child is on the block on the Planck, so the total mass of the system will be m plus capital M. Okay. And we assume, let us suppose the center of mass is somewhere here and its velocity is our VCM. So we can say that after collision the entire system is our m plus capital M moves with velocity of center of mass, which is our VCM. Therefore, we can say the final momentum, that is a PF, will be equal to our m plus capital M multiplied by VCM. Now from the conservation we can say our P initial is equal to P final, so which gives us our m naught V I unit vector is equal to m plus capital M, and this is our VCM. So from here we can find out our velocity of our center of mass will be equal to m v naught m plus capital M, and this is our I unit vector. So this is the velocity of our center of mass, and basically this is nothing but the translational velocity of center of mass. So you can say this is our translational velocity, and there is no, you can say, external force acting on it, so this is going to remain constant. Now let's find out the location of our center of mass of the system, because system is now m plus capital M. Location of center of mass of the system, and system is m plus capital M. Now in this case we are going to find out the system center of mass with respect relative to the Planck. Okay, and the Planck's own center of mass is L by 2. Okay, and the child is at position y is equal to 0. Okay, because it is right at the end, and the Planck's center of mass is at L by 2. Therefore, we can say that the system center of mass, or let me write it here, that the Planck's center of mass will be y is equal to L by 2, and we know that our child is at y is equal to 0. Therefore, we can say that y of our center of mass will be equal to m times 0, that is our distance, plus mass of the Planck and its distance, and divided by total mass. So this comes as our ml, and this is twice m plus capital M. Okay. So this is distance from the child. Okay, so you have to remember this is distance from the child, and distance from the Planck's center of mass we can easily find out now. So we know, let me draw it here once again. So child is somewhere here, and the distance of the center of mass from the child is our YCM, and the Planck's center of mass is somewhere here, and its distance is our Y. So we have to find out the distance of the center of mass of the system from the center of mass of the Planck. Means we have to find out this distance, and let us call this distance our delta. So obviously that will be y minus YCM. Therefore we can say that our distance of center of mass, system center of mass, distance of system center of mass from the Planck's center of mass, and that is our delta, which will be equal to y minus YCM, and we simply substitute the values. We get delta is equal to y is our L by 2, YCM we just calculated is our m L upon twice m plus capital M. And now it is quite easy to solve. L by 2 we can just take as common, so this comes as our m plus capital M minus capital M divided by m plus capital M. Here this m and m cancel out, it means Planck's mass cancels out. Therefore we get that this delta will be equal to, we get this as our ml twice m plus capital M. So this is our the distance which were asked in the our okay. So we found out our center of mass from our Planck's center of mass. now we come to the conservation of our angular momentum. Conservation of angular momentum. And because there is no external torque, there is no friction, so the angular momentum about the system's center of mass is going to remain conserved. So we have to remember that this angular momentum is with respect to the center of mass of the system. And let's start with our initial angular momentum about the center of mass. Initial angular momentum about center of mass. So Planck was at rest, so its angular momentum at initially will be equal to 0. So we know that Planck is at rest, therefore its angular momentum is equal to 0, and the child velocity is, you can say, perpendicular to the line from the center of mass, okay? Because the line coming from the center of mass is along y-axis and the child velocity is along x-axis. Okay, so these both are perpendicular to each other. Therefore, and YCM we already know, therefore we can find out the child initial angular momentum. Okay, we already calculated our YCM, that is our ml. Okay, so this is our YCM and child is moving perpendicular, so this is our child. Therefore we can say that our the perpendicular distance of the or let's call this as child initial angular momentum and about center of mass, and we can call this as L initial, will be equal to, that is of m v naught times our YCM, and YCM we already know, and so we get this as m times v naught, and YCM is ml upon 2 m plus capital M. And so initial angular momentum is only because of the child, because the Planck was at rest. So entire initial angular momentum is our Li. Now we come to our final angular momentum, and the final angular momentum is, you can say, the system is rotating as a rigid body and about its center of mass with the angular momentum omega. So we come to our final angular momentum, and about center of mass, and center of mass is about this point. And we know that after collision, the system rotates as a rigid body about its center of mass, and with angular velocity omega. That is our omega. So it is going to along this, it is going to in this direction omega. And in this case we have to remember that we are talking about the center of mass of the entire system, not of the Planck. If you can say the child was not on the Planck, then we are going to discuss this everything with respect to the center of mass of the Planck. Now we are discussing the center of mass of the system. That's why we have taken here YCM also. Okay. And so you can say that our final angular momentum will be equal to moment of inertia of our with respect to center of mass and its angular, that is omega. Okay. And this ICM is of the entire system. Okay. So we have to remember this ICM is for our combined system. Okay. So we can easily find out this ICM, and so we can say our moment of inertia, that is our ICM. And for that, this we can just say that the child is like a point mass and it is at a distance YCM, and we know that our Planck is at a own center of mass is it is 1/12 ml square. Okay. Therefore we can use our parallel axis theorem to find out the Planck's moment of inertia about the system center of mass. So we are interested in moment of inertia of the center of mass, and this is our combined system. Okay. And for that we can once again draw the figure, and we know that if this is a center of mass of the Planck, it's a Planck center of mass, and this is our system center of mass. We already know, because the length is given as L of the Planck, we already know that the Planck's moment of inertia of the Planck about its own center of mass. This formula we know, and then we are going to use parallel axis theorem, because this distance is our delta, and we are going to find out the moment of inertia of this Planck about the system center of mass. Okay, so this is the basic thing which we are going to use here. So we know that Planck's moment of inertia about its own center of mass, and that is equal to 1/12 ml square. And then we are going to use parallel axis theorem. so that we get Planck's moment of inertia about the system's center of mass. So we can say the moment of inertia of the Planck will be equal to moment of inertia of the Planck about its own system center of mass plus mass and distance square between them. We already know about delta, therefore we get this moment of inertia of the Planck will be equal to, okay, Planck is across this system, so this is our moment of inertia of the Planck, and we substitute the values. This is our 1 by 12 ml square plus this is a m delta we calculated is our ml upon m plus m plus capital M and its whole square. Okay. And now we find out the child's moment of inertia about the center of mass. Okay. And child is, we can say, somewhere here, and this distance we already know is our YCM. So we can say that our child's moment of inertia about the center of mass, and that will be equal to, let us suppose our I child will be equal to its mass and YCM square, MR square. R is here is YCM. So we get our I child will be equal to M times YCM is our ML twice M, and this is our whole square. Now we can add both our Planck as well as our child. So we get our total ICM will be equal to for our Planck plus for our child, and here this is same in both parts, so we can just take it as common. Okay. And let's substitute it and then we can solve it, because it is only the solution is left, rest is done here. So we get this is equal to, and 1 by 12 ml square plus capital M. Okay, rest is same. So we have this as ml plus twice m plus capital M whole square plus small m ml twice m plus capital M whole square. One second, there is some mistake. YCM, what was YCM? YCM was our capital M. So this comes as our capital M, and here also side is our capital M, and sorry, that is our delta. Delta is our small m, yes, and this is delta, that is our small m. That was mistake on my part, and therefore this will be a capital M, so we cannot take it as common. Okay, and it is small, and another one is a capital M. And let me give the solution directly, otherwise it is going to take a lot of time. There is no purpose of doing that. So I can say that my ICM will be equal to, this will be M L square 4m plus capital M divided by 12 m plus small m. So this is our the moment of inertia of the system about its center of mass. So you can say about system's center of mass. Now we can easily find out our angular velocity because we are going to use the conservation part. So we can say that conservation of angular momentum, because we were only missing here of ICM which we calculated, so this comes ICM times omega is equal to our initial. Therefore we can write that our ICM times omega is equal to m times v naught, and this is a ml upon twice m plus capital M. And we can say that our omega is equal to, this comes as m v naught upon ICM, and this is ml upon twice m plus capital M, and we substitute our ICM, so we get this as our m v naught. ICM is our ml square 4m plus capital M divided by 12, and this is our m plus capital M, this is multiplied by ml, and this is twice m plus capital M. And here we can cancel out this m plus capital M plus capital M, and this 12 goes by 6, and this m cancel out with m, square goes by this L. Okay, so most of things goes away, so we can say our omega is equal to, we can take 6 inside the numerator, so this comes as 6 m v naught, and we are left with L times 4m plus capital M. So this is our angular velocity, okay, of the system. Now in the part B it states that location of the point on the plank which is at rest immediately after the collision. Okay. So after the collision means we are talking about the system. Okay. And so we can say that there will be a point on the plank, or we can say of the system rather, that is nothing but our vector sum of our translational velocity as well as rotational velocity relative to the center of mass. Okay, so we can say that. So we can say our part B And for part B, you can say that velocity of any point on the any point of the system, any point of the system is vector sum of center of mass translational velocity and rotational velocity relative to center of mass. So we can easily find out their respective velocities. So let's find out the general expression for the velocities. And for that, let us assume that there is a point on the system which is at a distance y from the end. So means, so this is our end. From here we can assume at any point which is at a distance y. And so we consider a point at position y. Okay. And therefore we can say that the relative position relative to the center of mass, position relative to center of mass, let us call this as r, and this r will be equal to y minus ycm. Okay. So this is a position with respect to our center of mass, and obviously in the direction of our y, that is our j unit vector. Therefore we can write that our translational velocity so we can say our translational velocity, which is our velocity of our center of mass, which we already know, that is our m times v naught and m plus small m, and our I unit vector, because that will be same along the constant basically. Now we come to the rotational part. So you can say rotational velocity and rotational velocity, let us call this as our v rotational, which will be equal to our angular and our r position vector, which was just calculated. Okay. And so from here we get rotational will be equal to omega is our in k unit direction, and this comes as y minus ycm, which is in j direction. So this is our k cross j, which will be basically minus of w, and this comes as y minus ycm and our I unit vector. Okay. So it will be opposite to the direction of our vcm. That is the only purpose of this negative sign. So therefore we can say total velocity at y total velocity at y will be equal to, let us call this as our v of y, and that is a vcm plus v rotational plus v rotational. So we get v of y is equal to m times v naught m plus capital M minus omega y minus ycm, and both are along I direction. And like we said that it is asking the question part B, that is this is equal to 0. So we substitute this is equal to over 0, and we can set this will be giving us our y minus ycm will be equal to, and minus minus will be plus, so this we get as mv naught, and this we can just write it and divided by omega, and the numerator is nothing but our velocity of center of mass divided by omega. And we know both our vcm as well as omega, so we can just substitute them, or let me keep as it is. Why I am making it complicated? So this comes as our m times v naught m plus capital M multiplied by omega. So this comes as our mv naught m plus capital M and divided by omega. So 1 upon omega we know is our 6 times mv naught divided by L 4m plus capital M. And here this mv naught cancels out, and rest is going to remain same. So we get this as our y minus ycm will be equal to, we can take this in the numerator, so this becomes L 4m plus capital M, and this is 6m plus capital M, and mcm, this ycm we also know, therefore we can say y is equal to, this will be our L 4m plus capital M 6m plus capital M plus ycm, and ycm is our ml, and this is twice m plus capital M. And we can take we can write that y is equal to, we can take common, and common will be our L upon, this comes as our 2m plus capital M, and inside we are left with 4m plus capital M divided by 3 plus, and we are having a capital M. So this will be coming as 3m gives us 4m, so this will be n, this is 2m plus capital M multiplied by, we can take 4 as common, so this comes as m plus capital M, and this is divided by 3, and we have this m plus cancel out, 4 goes by 2, therefore we get that our y is equal to 2L divided by 3. So this point is going to have our velocity is equal to 0, and this point is with respect to our child. Okay, that's the lower end. From the upper end, we can just minus it by L, that will be coming as L by 3. Okay, so this completes the. Now we come to the next question, and this question states that a wheel with fine teeth is attached to the free end of a light horizontal spring of constant K, unstretched length L. The wheel has a mass capital M and radius capital R, and all of its mass is concentrated on the rim. Okay, so that is given to us. 1 second. And so here we are given two positions, which states that for the position x greater than L, we are having the wheel slips freely on the surface, no rotation. And for x less than L, the wheel's teeth mesh with the teeth of the ground, preventing slipping. The wheel then rolls without slipping. So this is basically, you can say, condition for slipping and no slipping. Okay, rotation and slipping motion. Okay, that's why it is given a teeth, otherwise it doesn't matter. Okay, it is only the to now differentiate between the pure rolling motion and only the slipping motion. So based on this, we have two questions, three rather. The wheel is pulled to a position x equal to L plus B and released from rest. How close will it come to the wall on first trip? Part B, how far out will the wheel move after leaving the wall? And part C, described what happens when the wheel next engages the tooth gear track. So the question language is a little bit complicated because of this mention of this tooth gear. Otherwise it is only based off whether there is a pure rotation or when there is slipping. That's the only difference. That is only the purpose of this tooth. So we can, in simplest term, we can say that it is basically a wheel spring problem with slipping and rolling transition. That's the simplest form we can write this problem. So you can say that this is basically our wheel on spring problem with slipping or rotation transition. Transition means it is going to, we can say, move from rotation to slipping, then back to slipping to rotation, and this is going to is a transition motion depending upon value of the position. Okay, if it is greater than L or it is less than L. So this is the simplest form. We can explain it, forgot about everything, the gear and everything. And so let us write what are the things given to us. So we are given that we have a wheel and its radius is R, is given as capital R. Its mass is our capital M, and it is given that all the mass is at the rim, so we can say its moment of inertia, that is our I, is equal to our mr square. Okay. And okay, so let me write here two things. First is when my x is greater than L, so under this condition the wheel slips. So if there is wheel is going to slip, So there will be only translational kinetic energy. Translational kinetic energy. And we have our when x is less than L, then the wheel meshes with the teeth. Wheel meshes with teeth, and which basically means rolls without slipping. Here teeth is nothing but is you can say playing the part of the friction. So we can say rolls without slipping. And if it rolls without slipping, so obviously we can say that V is equal to R multiplied by omega. And we can also say that our kinetic energy will be our translational plus rotational. So this is the basic premise of this entire question. And we have to find out in the first case when it is stretched how close it comes to the wall. So basically it depends upon the value of our length L. And so for that, let us understand the assign the coordinate and sign system, and we assume that suppose this is the wall and we have a spring. To the wheel we will come later on, and this wall we assume that this is our origin. So we have our x-axis and our y-axis. So we are given that length L is unstretched length. Okay. And one second. Okay, it's pulled to the position of x is equal to L plus B. So if this is our unstretched length, let me call this our length L, and when it is being stretched, so it will be something like this, somewhere here, and this will be L plus B. This is our unstretched, this is our stretched length. And you can say that our at, because here this coordinate will be our x is equal to L plus B, which is given in the question also. So we can say initially at x is equal to L plus B, our V is equal to 0, and obviously omega will be also equal to 0. And let us divide now according to the region, that is whether x is greater than 0 or whether x is less than 0. So entire discussion will be based on that. So we have our initial motion, and initial motion is x greater than L, and we know that when x is greater than L, there is slipping. So we know that our x is greater than L, so because there is no teeth or there is no friction. Okay. Teeth is nothing but our friction. We have to remember that our teeth is equivalent to our friction. So initially when x is greater than 0, so we can say there is no friction, and if there is no friction, we know that there is no torque, and if there is no torque, we can say that our omega is equal to 0. Okay. And like we said, that motion will be purely translational. Therefore, we can say that it is simple spring which is connected, it is just like a mass connected to spring. That is our. So based on this, we can write that our, okay, I have to forgot to mention here one thing, that is our, okay, let me write it here, spring force that is of Fs will be equal to minus K, and this is x minus L. Okay, therefore we can write that for the motion x greater than L, we can write the equation of our this motion. So we can say our equation will be equal to mass into our acceleration. Acceleration we are going to take double derivative of x, will be equal to, because there is no other force, only spring force is there, so we get this as our minus K x minus L, and it's can generalize this, and one second. Okay, so its solution is a general one, which we can say that the solution of this can be written as our x of t is equal to L plus b cos of omega t, and from here we can find out our velocity, that is our v of t, its derivative, that is minus of b, this is our omega naught, so this is our minus of b omega naught and sine of omega naught times t, and our this omega naught will be equal to our spring constant divided with the mass and its square root. So we can say velocity at x is equal to L negative, just before coming to exact distance of our L. So we can say velocity at, or let us say that it reaches x equal L when our, if x is equal to L, so we substitute here, this L and L cancel out, this comes as 0, so we can say when our cos of omega naught t is equal to 0. and therefore from here we can say that T will be equal to our pi by 2 omega naught. And just towards the negative side, so you can say that our velocity at x is equal to just L negative, we can say that our V will be equal to, and that is equal to our, we substitute value of T which we just calculated will be equal to pi by 2, and sine pi by 2 will be equal to our 1. So that will be giving us minus b omega naught. So just in order to differentiate that it has not reached yet at L, okay, just to the right of the L. And we know our omega naught, so we get this as our minus of p and k divided by our m. Okay. And this we calculated, okay. And we can say that if our V naught is equal to b k upon m, therefore we can say V is equal to minus of our V naught. And therefore at this same point we can find out its kinetic energy. Therefore the kinetic energy at x is equal to L negative, which will be equal to our half m V naught square, and this comes as our half m V naught is our b k m square root and its whole square, and this comes as our square goes by this square, so this will be b square and m, so this comes as our half b square times k. And the potential energy at x equal to L will be our u is equal to 0. So this is our just coming right at our x equal to L. Now we come at exactly at x equal to L. That is, it is coming into the frictional part, or we can say the teeth as well as mesh are engaging. So you can say engagement at x is equal to L, or we can say entering meshed region. And as soon as it enters the mesh region, there is no slipping. Okay. Only you can say, I think we have just written also, that is there is rolling without slipping. Okay. So from here we can say that there is no slipping, and if there is no slipping, our velocity there is no slipping, therefore we can say that velocity of the contact point, that is a bottom point, will be equal to 0. So we can say there is no slipping, therefore we can say that, which means that at this position it is exactly at x is equal to L, and this is suppose our P point, therefore we can say that velocity of this P point will be equal to our 0. And if the velocity of our P point is equal to 0 and the linear velocity is now our v, and the angular velocity, our angular is our omega. Therefore we can write that our just before, that is our x is equal to L negative, we already know that our v is equal to minus of v naught. Okay. And our omega is equal to 0. Therefore we can write that velocity at our point P will be equal to our v minus omega times r, and that is equal to our minus v naught, because omega is equal to 0 and v is equal to v naught, so we get velocity of point P is equal to minus of our v naught. And there will be a impulse to the right at the bottom. So we can say that impulse j to the right at bottom. Bottom basically means our P point. Okay, so at this position there will be impulse j, which is going to provide the required torque so that it rotates. And we can find out the change in linear momentum. Change in linear momentum, and that is our m v prime is equal to m minus our v naught plus j. And from here we can write that our v prime is equal to minus v naught plus j upon m. And we can find out the change in angular momentum. Change in angular momentum, and that change in angular momentum will be equal to our I omega prime will be equal to I multiplied by 0 minus r times j, okay, which is basically our torque impulse minus rj. So from here we get that our omega prime will be equal to our minus rj upon I, minus rj upon I, and I we know is our mr square, so this comes as minus rj upon mr square, square goes by r, therefore we get that our omega prime will be equal to our minus j upon mr. And we know that for no slipping condition, no slipping condition, we know that our V prime should be equal to omega prime times R. Okay, this is a no slip condition, and we have to remember that all these this omega and V are just before entering the point P, and as soon as it at x is equal to L negative, and as soon as it becomes x equal to L, the velocity changes to our V prime, and this angular velocity changes to our omega prime. Okay, that is a major difference. And we substitute the values V prime and omega prime, so we get this as our minus V naught J upon M is equal to minus J upon MR times R, and here this R and R goes away. This comes as minus J upon M. So you can say that from here our J will be equal to, this is minus 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 is our plus 2J, and this will be twice, and we have our, okay, so this comes our MV naught and divided by 2. So this is our impulse. Now we can find out our V prime also. So our V prime is our minus, and V prime was our minus V naught plus J upon M, minus V naught plus J upon M. So this comes as minus V naught plus J is our M V naught upon 2. So this M and M cancels out, and this comes as minus V naught plus V naught upon 2. So this will be giving us minus twice V naught upon 2. Okay. And we can also write that our omega prime is equal to minus, this is V naught upon 2 times R. So we got our V prime as well as our omega prime. Now we can easily find out there the kinetic energy. So we can say our kinetic energy after will be equal to our rotational as well as translational. So this comes as our half V naught square and plus half I, and omega is our, because this is negative and anyway square, so this comes as V naught upon 2R whole square. Okay. So it is now, so this gives us, and so this is our translational and this is our rotational. So it will be coming as I, we also know that is our MR square. Okay, so we can say it is equal to M, we have a V naught square upon 4 plus half, and here we have our MR square times V naught square upon 4, and this is our R square. R square and R square cancels out, and this comes as 1 by 8 as well as our 1 by 8. So this is coming as our 1 by 4 M V naught square, and we can find out our energy loss. Energy loss will be equal to, our initial was our half M V naught square minus 1 by 4 M V naught square. So this comes as our 4 with our LCM and giving us 2 minus 1, that is our M V naught square upon 4. Okay. So this was our first, and we come to our next part, that is motion when x is less than L. So we have motion in x less than L, and so there is rolling without slipping. And most of things we have already calculated, and you can say that our total kinetic energy, one second, okay, so total kinetic energy is equal to over half m v square plus half I omega square, and this is equal to over half m v square plus, and this will be also coming as over half m v square. So okay, so let me write it this way. So this comes as a half twice m v square, and because the spring, one second, spring is having a mass now. No, spring doesn't have the mass. Okay, anyways, that's not a big problem. And so from here we can say that this twice m is the representation of our effective mass. And based on it we can write the equation, that our equation of motion and that of equation of motion is going to give us twice m double derivative, which is our acceleration, is equal to our spring force, and from here we get double derivative, and spring force is our minus k x minus L divided by twice m, and our angular frequency will be equal to our k upon effective mass, that is twice m and its square root, and our total energy will be equal to, let us call this our E, is equal to our energy associated with our spring, that is half k x minus L whole square, and energy associated with our, that is our kinetic energy, 2m v square. And we can say that this is equal to over m v naught square upon 4. This energy will be nothing but our constant. Okay, so most of things are sorted out. Therefore we can say at entry, that means at x equal to L, we already know that V is equal to our minus V naught upon 2, and the energy will be giving us, this term will be 0, So we get this as our m v naught by 2 whole square, which is our m v naught square by 4. Now we come to the part A. Most of the things we have already calculated. So we have our part A, how far it comes in the first trip to the, you can say, to the wall. That is basically, so we have to find out the minimum value of x. So we can say we have to find out the minimum value of x, and at minimum value of x we are going to get that the value of velocity will be equal to 0 and omega will be equal to 0, and we are also going to get its kinetic energy will be equal to 0. Therefore we can write that our half k x minimum minus L whole square will be equal to m v naught square upon 4, and we already know that our this x minimum obviously will be less than L. Therefore we can write that our x minimum minus L will be giving us negative of our m v naught square upon 2k and its square root. Or from here we can say our L minus x minimum will be equal to m v naught square upon 2k and its square root. We already know that our v naught is our k b square upon m, or we can say our v naught square is equal to k b square upon m. Therefore we get L minus x minimum is equal to m upon 2k times k b square upon m square root, and here this k, m and m cancels out, so we get this as our b upon square root of 2. Therefore our x minimum will be equal to L minus b square root of 2. So this is the minimum distance of our, that is our, it comes close to the wall. Now once again it is going to back to this meshed region and is going to de-engage at x equal to L. So after that, from here we can say that it returns to meshed region and disengagement at x equal to L. And obviously motion will be symmetric, therefore we can say our motion is symmetric so it means at x is equal to L positive we are going to have our velocity v will be equal to plus v naught upon 2, and we can say our omega will be equal to plus v naught upon 2r, and at disengagement means when x is equal to greater than L there will be no impulse. Okay, if there is no impulse, there will be a smooth transition. So it means velocities are not going to change. So you can say that at x greater than L, because there is no friction as x greater than L, there is no gear system. So we can say no impulse. If there is no impulse, we can say that our velocity is unchanged. So there is no friction also. So therefore our omega, so we can say our no friction. And if there is no friction, our omega will be going to remain same, that is our V naught upon 2R, and our kinetic energy rotational will be same. So we can say our kinetic energy rotational will be equal to, and that is our, I think we calculated it, kinetic energy rotational we did calculate it. Okay, no problem. We can calculate it if it's required. We'll keep it right, it is as it is. So let us find out our, or let me write it, because we are going to require it in the form of energy. So we can say our kinetic energy rotational will be equal to our m v naught square upon 8, because rotational will be equal to our half I omega square. So that will be giving us m v naught square upon 8, and then we can find out our, there will be translational motion. So we can say for the translational motion, we can write the equation, that is m double dot is equal to minus k x minus L, and we can also write the equation for our energy. So we can say our energy will be equal to energy because of the spring plus our half mv square plus we have our m v naught square upon 8. Okay. And this will be our m v naught square upon 4, which we have done previously also. Now it comes to how far will it go as it leaves the wall, that is our part B. And once again, at maximum distance, that is a turning point, our velocity V will be equal to 0. So you can say at maximum x, we are going to have V is equal to 0, which will be the turning point. Therefore, we can write that our half k x maximum minus L whole square velocity is equal to 0. So this terms comes as 0. So this will be our plus 0, and m v naught square upon 8 is equal to m v naught square upon 4. Okay, now it is simple calculation is left. So we get this as our half k x maximum minus L whole square is equal to, this will be minus 1 by 4 minus 1 by 8, and that will